Careful. You were just talking about hex, right? So, what's the smallest hex digit that is not zero?
F.
Huh? That's the largest.
Okay. The smallest.
What?
The smallest digit.
8?
8.
Well, the small a is 10. That God knows it's not the smallest. Must be smaller than 10, right? Well, 1. Right? Smallest non-zero digit is 1. Okay? And it's hex. 1. And you see, because of those lousy 3 bits here, the standard uses binary base as opposed to hex base because you lose 3 bits here. Right? So that's why the standard, there's some other reasons. You will see that the range here will be unbelievably larger. It's hard to express how larger, you will see. And paradoxically, the speed, you will tell me why, will be larger here, much larger too. And yet the standard uses that because we lose that, and also the distance between the two numbers, it's sort of the power of 16. So the numbers are less precise. This way, it's a little crude, but let me put it that way.
So could you represent that as hexadecimal? So you just put 1.
You can represent it as hexadecimal, but we're not going there. I don't want to.
Another word not to go down.
Remember Occam's razor, right? Don't bring the entities beyond the knee. And that's always in teaching, it's always very important. In other words, keep it simple, stupid. That was it.
And that's still 24 though, right?
Yeah, well, let's write it up, okay? The thing that changes here is what? Well, this is 16 to the minus 1. 1/16. Right? And that is 16 to the minus 64. Again, 16 doesn't show, it's built into the machine. Right? We don't have to show it. There are no machines that use that and this. At least I haven't seen one. Everything is possible. Right? In other words, 16 to the minus 65th. And that one is, again, 0, 1. Again, 7 ones. And again, all ones. Right? So in other words, what have we here? 16 to the power 63 plus, frankly, it's the same number. That number, whether it's a base of 16 or base of 2, it doesn't matter. It's the same number, but we'll be elegant and we'll say this is 16 to the minus 6, which is the same as 2 to the minus 64. Same thing. Simply we want to be consistent, just strictly for greater elegance here. If it doesn't matter because it's still as good as 1, and that's still 16 to the 63rd. Okay, now what is that to compare the ranges? What?
4 times as large?
Because we're talking power of 2. We have to go to the power of 10. In other words, this has to be multiplied by a factor because we're going to a lower power, right? So if we're going to the lower base rather. So if the base is lower, the power will be higher. And again, I happen to know that this is 1.2, right? This is 1.2 coefficient. So that is about 10 to the power of minus 76, and that is 10 to the power of 76. So it's like 150 zeros spot. Okay? So you can see the fantastically larger range. You cannot express it in human terms, but it's a fantastically larger range. Okay? Between the base of 2 and base of 16. Okay, so for this team we have the range, and for this team we have the speed. Now, how does the speed comes in? Well, remember when I was telling you about the addition? Are you a part of our thing?
No, I have to be a project in the company.
Wait, but are you running this course?
Yeah.
Okay. So you got to catch up, because.
Yeah.
All right, okay. A 10 to the power 76, whatever, where does the speed come? Remember, this is not about the representation. Representing is very nice, but it's about performing operations. I was just hinting to you, alluding to you on addition. When we add, we have to denormalize numbers, then we have to add, and then we have to renormalize the result. Now what the hell does it mean normalize, denormalize? That means shifting, right? If you shift, by how many bits do you shift? In this case, each bit is a digit. You shift 1 bit at a time. In that case, 4 bits at a digit. You shift 4 bits at a time. But God knows this is going to be much faster, right? So you have a greater, much greater range, much greater speed, and the standard is that, because that gives you greater precision. Now, remember, by the way, in general life, whatever you do, Six Sigma, whatever, the difference between precision and accuracy. Accuracy means how close do you come to a true value. You can be extremely precise, but you can be way off the true value. Right? So that number might look great, but it actually is more idiotic if it's very precise, but it is way off the true value. So from all of this conversation, we could not infer anything about the accuracy because we don't know anything about any true value. The true value is always contextual. It depends what you're talking about. Right? But here we are talking about the precision. In other words, the number of bits. Now, if I were to show you how the whole thing looks like on the number axis, it looks like that. That's a true zero, right? And those are the representable numbers. Okay, this is the representable range. And also this, true zeros, I said, it's all zeros, right? Now, actually it comes as close to the zero as I can show, right? But why can't we show those values? What is that? In computerese, what?
Infinity?
No, it's not infinity because that is a finite number. But it's overflow. This is overflow. In other words, the value of, it's good you're trying, the value of the exponent, the positive value of the exponent is very large. Here, the value of the number is negative, but the value of the exponent is positive both here and too large to be represented, right? Because again, we got 7 bits here, right? And that is the range of the exponent. Right? In other words, from minus 64 to 63. If it's minus 65, it falls in here, and that correspondingly is underflow. In other words, the number is too small to be represented. The negative exponent is too low. The negative exponent value is too large. Okay? All right, let's take a break. Why don't you take someone's notes now? Because you'll need it. Okay, take a break, then you can hit me with questions. We're not done. Thank you, sir. And I'll take over.